Welcome to the Depth Dive. Today, we're diving into the world of quantum physics, where, well, the rules of reality get a little fuzzy, to
Yeah,
say the least.
secret.
We've got a whole bunch of articles and research lined up, covering a range of topics from wave-particle duality to quantum entanglement. So get ready to explore really the fundamental building blocks of the universe and, maybe even have your mind blown a few times along the way.
What I think is really cool is that we're not just talking about some abstract theories here. We're dealing with concepts that are already being used in like cutting edge technologies that could
Yeah.
totally change the world as we know it.
Okay, let's kick things off with one of the most well-known concepts
hmm
in quantum physics, wave-particle duality. Now, it may sound kind of complicated,
hmm
but actually you've seen it in action tons of times. Think about light, for instance. Sometimes it acts like a wave, spreading out, bending around corners, like when you see those awesome rainbows through a prism.
Right, exactly. And then other times light acts like it's made of
Mm-hmm.
these tiny little packets of energy
Mm.
called photons, almost like super tiny bullets of light.
Mm.
And this duality, this
Mhm.
ability to be both a wave and a particle, it's not just limited to light either. Even electrons, those super tiny particles that
Mm.
zip around atoms, they do the same thing.
So, are they like tiny billiard balls bouncing around, or are they waves just rippling through space? How can something be both?
Well, that's the thing. They're not really either one, and they're kind of both at the same time. It all depends on how we look at them, how we observe them.
Sure.
Scientists have actually done experiments where they shoot electrons through two tiny slits. And
Yeah.
instead of getting two separate lines on the detector screen, like you'd expect if they were just particles, they got an interference pattern, which is what you see with waves.
Wow.
It's as if each electron went through both slits at the same time.
Wait, hold on. How can an electron be in two places at once? That doesn't make sense.
I know, right? It really challenges our everyday way of thinking. But that's what's so cool about quantum physics. It forces us to rethink what we thought was possible.
Right.
And it gets even weirder. If we try to, like, peek and see which slit the electron goes through, the interference pattern disappears. And they act like regular particles again.
So they know when we're watching. It's like they're playing a cosmic game of hide and seek.
Yeah, kind of. It
Yeah.
really makes you think about the role of the observer
Yeah.
and how just the act of measuring something can affect what you're measuring.
So it's not just about the particles themselves. It's about how we interact with them. It's like the universe is saying, hey, you're part of this too.
Exactly.
Wow.
And this leads us to another mind-blowing idea, quantum superposition.
Okay.
It's the idea that a particle can be in multiple states
Mm-hmm.
at the same time until it's measured. Imagine a coin spinning in the air. Until it lands, it's both heads and tails, right?
Right.
It's the same kind of thing with particles.
No. It's not that it's actually like quickly switching between states. It's actually in all of those states at the same time. It's like the universe is saying, make up your mind. And the particle's like, nope, not until someone's looking.
Yeah, something like that. And the really amazing thing is that this may-be state is what makes quantum computers
Mm.
so much faster than regular computers. They can explore multiple possibilities all at once, which opens up a whole new world of computing power.
Now, that's a really cool takeaway. This isn't just some theory. It's already leading to real-world applications.
Yeah.
Okay, let's add another layer of complexity to this. Let's talk about quantum entanglement. Now, if superposition is about one particle being in multiple states at once, entanglement is about two or more particles being mysteriously linked, no matter how far apart they are.
Right. It's like they share some secret connection.
Yeah.
Change the state of one entangled particle.
Yeah.
And the other one instantly reflects that change, even if they're light years away.
Or are they communicating faster than the speed of light? Isn't that supposed to be impossible?
Well, that's the big mystery with entanglement. It seems to break the rules of classical physics. Even Einstein wasn't a fan of this. He called it spooky action at a distance.
Spooky action at a distance.
But you know what? Countless experiments have proven that it's real.
Wow. So what does this spooky connection actually mean for us? Could we use it to like teleport ourselves or send messages across huge distances instantly?
Those are great questions. Scientists are definitely looking into using entanglement for things like
Yeah.
super secure communication, where the information is protected because of that special connection
Mm-hmm.
between the particles. And yeah, even teleportation, at least of information, is something that's being researched.
Okay, so we've got particles acting like waves and particles existing in multiple states at once and mysteriously linked across huge distances. It's like the universe is playing by a whole different set of rules, rules that we're only just beginning to figure out.
And there's more to this. It's not just that these particles are playing by their own rules, but even the rules themselves are kind of blurry. Let's talk about the uncertainty principle.
Okay, hit me with it. I'm ready for more mind-bending stuff.
All right. Imagine trying to track a tiny, super fast hummingbird darting around a garden. You'd need a pretty good camera to catch it, right?
Oh, yeah, for sure.
But the second you snap a photo with like a bright flash, you might scare the bird and make it change direction.
I see where you're going with this. By observing it, I might actually be affecting it.
Exactly. And that's kind of like what happens in the quantum world with the uncertainty principle. Basically, it says you can't know both a particle's position and its momentum, which is like its speed and direction, with perfect accuracy at the same time. The more you know about one, the less you can know about the other.
So it's like a cosmic game of peekaboo. If I get a glimpse of where the particle is, then its movement becomes a blur. And the other way around. Is this because our instruments aren't good enough? Or is there something more fundamental happening here?
It's not about the limitations of our tools. It's a fundamental rule of the universe. At the quantum level, this inherent fuzziness, this uncertainty, suggests that reality, at its core, isn't made up of fixed, solid objects. With definite positions and movements, it's more like a realm of possibilities, a dance of probabilities.
So instead of neatly defined particles, we have this cloud of maybes constantly shifting and swirling. It's a completely different way of looking at things.
Exactly. Now let's shift gears a bit and talk about quantum field theory, which takes this idea of a fuzzy, probabilistic reality even further.
Quantum field theory, it sounds kind of intimidating, but I'm curious.
Well, it's actually quite elegant. And once you understand the main idea, imagine there's this invisible ocean all around us.
Yeah.
But instead of water, it's filled with different fields for every kind of particle, like an electron field, a photon field, and so on. And these fields are always there, even in the seemingly empty space.
So it's like this cosmic soup of potential particles just waiting to emerge.
That's a good way to think about it. And when energy is added to these fields, they get excited. And that's when particles pop into existence, kind of like ripples on the surface of this invisible ocean.
So the particles we see aren't actually solid little balls, but rather these fleeting disturbances in these energy fields.
Exactly. Quantum field theory suggests that particles are more like waves of energy, dancing in these fields, constantly appearing and disappearing. This concept also helps to explain how forces like magnetism and gravity work at the quantum level.
It's like these fields are the stage, and the particles are the actors in this grand play of the universe. But there must be some rules to this play, right?
Of course. That's where the idea of quantization comes in. In the quantum world, energy doesn't flow smoothly, like a ramp. It exists in specific levels, like steps on a staircase.
So no sliding down the energy ramp. You got to take it one step at a time.
Precisely. Electrons in an atom can only occupy specific energy levels, like those steps. They can't just exist anywhere in between. To jump to a higher level, they need to absorb a specific amount of energy, called a quantum, kind of like putting exact change in a vending machine to get your snack.
No change, no energy boost. So these energy levels are like the currency of the quantum world.
Exactly. And the size of these energy coins is set by a very special number called Planck's constant. It's incredibly small, but acts like the universe's measuring stick for energy.
It's amazing to think that something so tiny can have such a huge impact on how the universe works.
Yeah.
But okay, how does all this chunky energy actually show up in the real world?
Well, it explains a lot of everyday phenomena. For instance, have you ever wondered why we see such vibrant colors all around us?
Yeah, I guess I never really thought about it.
Well, it's directly related to this quantized energy. Atoms emit light in specific colors. Because when an electron jumps down to a lower energy level, it releases a photon, a tiny packet of light. And the color of that light depends on how big of an energy jump the electron made. Bigger jumps make bluer light, and smaller jumps make redder light.
So the colors we see are like a visual representation of these energy transactions happening at the atomic level. It's like the universe is putting on this light show based on these quantum leaps.
Exactly. And this precise control of energy levels, thanks to quantized energy, is also the principle behind lasers.
Wait, really? So lasers, which we use for everything from scanning groceries to doing eye surgery, are a direct result of these quantum principles?
Absolutely. Lasers work by stimulating atoms to release photons of a very specific energy, all in sync, which creates that highly focused beam of light.
Wow, that's incredible.
Now let's rewind a bit and revisit light for a moment. It played a key role in a few important experiments that helped shape our understanding of quantum physics. One of them is called the photoelectric effect.
Okay, bring on the light.
Imagine shining light on a metal plate. Scientists thought that the light's energy would gradually push electrons off the surface, regardless of the color of the light.
Okay, that makes sense.
But that's not what happened at all.
Really? What happened instead?
Only certain colors of light, the ones with higher energy, like blue or ultraviolet, could knock electrons loose. Red light, even if it was super bright, couldn't do it.
That's so strange. Why would the color of the light matter?
It was a big mystery. And it was Einstein who figured it out. He proposed that light wasn't just a wave, but also a particle made up of these tiny packets of energy called photons. And each photon carries a specific amount of energy based on its color or frequency. So blue light photons have more energy than red light photons.
So color isn't just about what we see. It's a code for different energy levels in the quantum world.
Precisely. And because photons come in these discrete packets of energy, they can only interact with electrons in certain ways. It's like trying to pay for something with a dollar bill, when the vending machine only takes quarters.
I see. So a red light photon just doesn't have enough energy to knock an electron off the metal plate, no matter how many photons you shine on it.
Exactly. It's like trying to move a boulder with a feather.
Okay, that makes sense.
Now, there's another experiment that really solidified this whole idea of quantized energy: black body radiation.
Black body radiation, that sounds pretty intense.
Well, think about an object like a piece of iron. As you heat it up, it starts to glow. First red, then orange, then yellow, and eventually white hot. This is called black body radiation. And classical physics couldn't explain why there was a limit to how much high-energy radiation the object emitted.
So classical physics was predicting that the hotter the object got, the more energy it would radiate, possibly without any limit.
Yeah, pretty much. It was a huge problem. And then Max Planck came up with a pretty radical solution. He proposed that energy isn't continuous, but comes in these discrete packets or quanta. And he introduced Planck's constant to describe the size of those packets. This idea not only explained black body radiation, but also laid the foundation for the entire field of quantum mechanics.
So Planck's solution wasn't just a fix for one specific problem. It was a complete shift in how we understand energy itself. It's amazing how these abstract concepts can have such profound implications for our understanding of the world.
It really is. And we can't leave out the granddaddy of all quantum mind benders, the double-slit experiment.
Yes, the experiment that makes you question reality itself. We touched on it earlier with electrons, but I'm definitely ready for a deeper dive.
All right, let's do it. Picture this. We're shooting particles, like electrons,
Yeah.
at a wall with two slits in it. Logically, you'd think we'd see two distinct bands of particles hitting the detector screen behind the wall, right? One for each slit.
Yeah, that seems pretty straightforward. Each particle goes through one slit or the other, creating two separate lines.
That's what classical physics would predict. But the results are far from ordinary. Instead of two bands, we get an interference pattern, like you see with waves. It's as if each particle went through both slits at the same time, interfering with itself.
Wait, hold on. How can a single particle go through both slits simultaneously? Are they multiplying, splitting? I'm so lost.
I know, it's crazy. And it gets even weirder. When we try to observe which slit the particle goes through, the interference pattern disappears.
Yeah.
And we just see the two distinct bands. Like, they suddenly decide to act normal.
So they know we're watching. It's like they're thinking, oh, someone's looking, better behave. This is just blowing my mind.
It's one of the clearest examples of how observation itself seems to influence reality at the quantum level. It challenges our ideas of objectivity and makes us wonder about the role of consciousness and shaping reality.
So are we, as observers, somehow influencing the outcome of these experiments? Are we creating reality just by looking at it?
That's a question that's been debated by physicists and philosophers for a long time.
Okay, so we've covered the dual nature of light, quantized energy, the uncertainty principle, and the mind-bending implications of the double-slit experiment. It's been quite a journey. But what does all this actually mean for us in our everyday lives?
Well, you know, these quantum concepts might seem kind of abstract and removed from our daily lives, but they actually have very real-world implications. I mean, think about it. From the lasers in our CD players to the transistors in our smartphones, quantum physics is at work all around us.
Wow, I never really thought about it that way.
And its potential is only just beginning to be explored.
It's like we've been living in this world built on classical physics. And now we're getting a glimpse behind the scenes, realizing there's this whole other set of rules governing reality at a much deeper level. And it's not just about understanding the universe, right? It's about using this knowledge to create new technologies.
Exactly. Quantum physics is already leading to breakthroughs in fields like medicine, materials, science, and even artificial intelligence. Quantum computers, for example, have the potential to revolutionize how we discover new drugs, design new materials, and even understand the human brain.
That's incredible. It's mind-blowing to think that these ideas that seem so bizarre and counterintuitive about reality at the tiniest scales could have such a huge impact on our world.
It is pretty amazing. And what's really exciting is that we're really just at the beginning of this journey. Quantum physics is a rapidly evolving field with new discoveries and interpretations popping up all the time.
So we've gone on this deep dive into the quantum realm, encountering particles that completely defy our everyday intuition. We've seen how they can be in multiple states at once, how they can be linked across vast distances, and how even just observing them seems to play a role in shaping reality.
If we had to boil all of this down, what are the biggest takeaways? That's a great question. I think the most important takeaway is that reality is far more complex and interconnected than we ever imagined. It's not just a bunch of separate objects, but a dynamic web of possibilities, probabilities, and connections. At the quantum level, the universe is more like a fluid dance of energy than a static collection of things.
That's a beautiful way to put it.
And this isn't just some abstract philosophical idea. Quantum physics has real practical consequences. It's not just about understanding the universe. It's about harnessing the power of the quantum world to create new technologies that can improve our lives.
And the future of quantum physics is full of possibilities.
It really is an exciting time to be alive, to witness all these developments unfold.
Speaking of exciting, there's one question that always seems to come up when we talk about quantum physics, the elephant in the room, so to speak. And it has to do with the role of consciousness. Could our thoughts, our observations, our very consciousness be influencing these quantum events?
It's a question that has fascinated physicists and philosophers for decades. Some believe that consciousness might be a fundamental part of what causes the wave function to collapse, which is the mathematical way we describe a particle's state, in which possibility becomes reality. Others say it's a purely physical process with no need for consciousness.
It's a truly mind-boggling concept to think that our minds could be intertwined with the fabric of reality at the quantum level. It's almost like we're all tiny quantum observers, shaping the universe with every thought and perception.
It's a profound idea, and there are even theories out there that suggest the universe itself might be conscious, like some kind of giant quantum mind. But these are still speculative ideas. There's no scientific consensus on the role of consciousness in quantum mechanics.
Well, as we wrap up our deep dive into this fascinating world of quantum physics, here's something for everyone to think about. If reality is truly a dance of possibilities, and our observations play a part in determining which of those possibilities actually become real, what does that mean for us, for our lives?
Could our thoughts, beliefs, and intentions be influencing the reality we experience at a quantum level? That's a really deep question to consider, one that might lead you down your own path of exploration.
We've barely scratched the surface of this amazing field, and there's still so much to learn and explore. Who knows what other incredible discoveries are waiting for us as we continue to delve into the quantum realm. So keep questioning, keep exploring, and never stop being curious about the universe and our place in it.
Thanks for joining us on this deep dive into the quantum world. Until next time, keep those minds curious and those imaginations ignited.